Hello, I'm Emma, and this year I've been working on a project looking at globular clusters in our galaxy, the Milky Way. The main aim was to try and figure out if young analogues of these systems are observable today. Firstly, I should tell you a bit more about our galaxy. So, the Milky Way is a typical spiral-type galaxy that consists of various components, including a bulge, a disk, and a stellar halo. Throughout these different components, there are around 150 globular clusters that are known to exist. A globular cluster is just one type of star cluster and is made up of millions of old stars that are gravitationally bound together in a roughly spherical distribution. The orbits of these systems can be seen on the left in the animation here. Each star in the cluster orbits the common centre of gravity, and then the cluster itself orbits the galactic centre. Globular clusters can be found not only in our galaxy, but in galaxies of all different types and sizes. Now, the different components of our galaxy are thought to have formed through different mechanisms over its lifetime. Galaxies as a whole are thought to form and evolve by the build-up of smaller systems as they merge, like for example shown in the animation on the left. Since globular clusters can be found throughout the whole of our galaxy, and they are old with age estimates on the order of the age of the universe, then as a system they are vital for furthering our understanding of our own galaxy's formation and evolution. If we look at the globular clusters of the Milky Way in terms of metallicity, as shown on the right, we can see two clear distinct populations. The central metal-rich population is theorised to have formed with the galaxy itself, whereas the metal-poor halo globular clusters are thought to have been accreted from other galaxies through merger interactions in its past. While as a system, globular clusters are important for understanding our own galaxy's formation, their own individual formation still remains a bit of a mystery. And so this is what we need to try and tackle first. Since the scale of the universe is so large and light travels at only one set speed, when we image a really distant source at what is called a high redshift, we are actually seeing how this source looked when the light was emitted, and therefore observations at high redshift can be thought of as looking back in time. This makes them really important for finding young globular clusters that formed in the early universe. Many studies, such as the example shown here by Van Zeller et al. 2017, have found potential young globular clusters through observations at high redshift. However, it is then difficult to determine if these young star clusters will actually evolve to resemble the globular clusters that we see in the Milky Way today. This is where my study comes in. I wanted to first determine the properties of a selection of Milky Way globular clusters, and then use these properties to model how they would have looked like when they had first formed. I can then produce images of these young clusters and place them at high redshifts to test whether they would be observable. For this study I chose 6 globular clusters, spread both spatially through the different components and also spread in different properties such as age and metallicity, so that they represent the whole of the Milky Way population. For each of the clusters in the sample, Hubble Space Telescope images were retrieved from the archive in various filters. These were then used to produce stellar catalogues, which were used to construct colour magnitude diagrams, like, for example, the one shown here. These are made by plotting a star's colour, which is the difference in magnitude between two filters, against the brightness, which is the magnitude in just one filter. A star's colour relates to its temperature and also to its mass, and the mass of a star dictates the position in the colour magnitude diagram. For globular clusters, we can assume a simple stellar population so that all the stars are of the same age. All the stars start on the main sequence fusing hydrogen into helium, but the more massive stars use up their fuel quicker and move on to shorter branches of evolution, such as the red giant branch and the horizontal branch. Since the mass relates to the main sequence lifetime, any star that has mass past the turn-off point mass must have a lifetime shorter than the age of the cluster. Therefore, the lifetime of the most massive star still in the main sequence can be used to find a lower limit for the age of the cluster. Using this understanding and the colour magnitude diagrams produced, we could then determine the properties of the clusters, including their age. To do this, we use stellar isochrones that represent a simple population of stars of a specific age and metallicity. This matches what we assumed in our simple model of globular clusters. We attempted to fit these isochrones to the binned colour magnitude diagram data using a chi-squared fitting method and finding those within 1 sigma of the best fit. These are shown shaded in blue, and the median properties of these are what are taken to be the property estimates for the clusters, all of which are in good agreement with the literature. With the properties determined, I then used modelling and various relationships to create images of how these clusters would have looked when they had just formed. This was done star by star. Firstly, a mass was chosen for the star according to an initial mass function. This initial mass function is produced assuming a certain slope, such that there are more low mass stars than high mass stars in the cluster, and the normalization is set from the total mass today from literature, and then extending down to the high mass stars that are no longer present in today's clusters but would be present had it just formed. For that mass, a temperature is then found from a specified range according to a mass-temperature relationship that we derive. The range is chosen to reflect the real-life variation in stars for each different mass, whilst also making sure that the stars remain physical so that the temperature and mass are still intimately connected. Then, with that temperature, a black body curve is produced, which represents the star's spectrum. The spectrum is then placed at either the distance the cluster is at in the Milky Way today, or the luminosity distance that corresponds to the high redshifts that we wanted to investigate. The spectrum is then convolved through the various filter profiles to obtain fluxes and magnitudes which give us a quantitative measurement of the brightness of the star. Finally, each star is given a position according to a probability distribution derived by modelling the cluster as a Gaussian distribution using the half-mass radius from literature. This means that more stars will be in the central regions and the core, and less in the outskirts, as seen in reality. The star is then placed in the images with the size of the point spread function measured from the original Hubble Space Telescope data. And then this is repeated for the total number of stars in the cluster, which was found from integrating the initial mass function over all masses. Here are some of the first results of generating these images. The example shown here is a Young NGC 6441. The images have been created of this cluster at the distance it is at today in the Milky Way, but as it would appear if it had only just formed in the last couple of mega-years. On the left we have the RGB colour image, which is created by combining all three filters together, which are shown individually on the right. The images do resemble a globular cluster today, but brighter and more massive since it is younger. Although there are now high-mass stars included in the cluster, the majority of stars are still the low-mass stars that peak in filters of higher wavelengths, such as 606 and 814, as can be seen on the right. Once we had generated the images of the clusters at the Milky Way distance and checked that this had worked, we could then use this same modelling to produce images of the young clusters but at high redshift. We chose to place the clusters at a redshift 2 and redshift 6.6, as these span the epoch of the universe in which the clusters likely formed when we take into account the lower and upper bound errors on the age estimates derived previously. At high redshift, the cluster can be represented as a single point source, so instead of placing each individual star in the image, we can sum the flux of all stars and just place one single source, because at high redshift, due to the scales and the distances, we are unable to resolve individual stars. And so this is why we get the images like you can see on the right here. We find that all of the young clusters in the sample are around 1.5 times more massive at formation than they are today in our modelling. This is because we only take into account the loss of stars due to stellar evolution. But if we were to include other factors such as the dynamics, then this value would be higher and possibly be in better agreement with previous literature. Currently, the deepest observations possible with the Hubble Space Telescope give a limiting magnitude of 29. And since magnitude is on an inverse scale, a source with a higher value than this is actually fainter and not observable. Shown on the right, you can see the rest frame UV images of young NGC 5139, which is the most massive cluster in the sample and hence the brightest. However, both at Redshift 2 and 6.6, the cluster is too faint to be observed by our modelling, at least currently with the Hubble Space Telescope. However, it could be observable with the upcoming James Webb Space Telescope. In summary, we were able to successfully measure the properties of Milky Way globular clusters. Coupled with modelling, we then managed to generate how these clusters would have looked when they were much younger. Images were produced of these young globular clusters at the distance they are at in the Milky Way today, and also at high redshifts of 2 and 6.6. We find that unfortunately even the most massive is not currently observable with the Hubble Space Telescope. However, there are many improvements that could be made to the modelling, such as including mass loss due to dynamical processes, and also investigating changing the slope of our initial mass function. These changes could mean that the young globular clusters are more massive and likely bright enough to be observable at high redshifts, which would be revolutionary for understanding more about star cluster formation. Thank you for listening.